So the plan for today is we're going to start talking about Bayesian hierarchical modeling. Last time we were talking about a video created by Josh, and hopefully you got a big idea of why we want to do it, and maybe roughly also how we can do it. From today, we're going to break it down slowly, and then looking at the details more, why you want to do it, how you can do it, and then still in the framework of trying to do something related to the normal model. I know Josh's video is also normal, but the mean itself has a more complicated structure with the power function, et cetera, et cetera. So we just gonna work from the regular normal modeling that we have done before, but now we're gonna start to think about how to put priors in a hierarchical way, especially if you have groups that you want to share information about. Okay. All right. So this is okay. So to get us started, I'm using a data set which is actually collected a few years back by a student in the same class, and she was doing a project. You're going to see it about Korean drama ratings. So it's continuous outcome about ratings of drama. And then I'm going to introduce you to the data set and then have a small discussion about what if you have observations in groups. So different approaches to modeling. And then, of course, we're going to, in the end, arrive that we should do hierarchical modeling and why that is the case. So once we get covered that, third part is how you can. So I'm using the word as two-stage prior just to convey the idea that we're doing the two-stage, but then everything come up as a hierarchical structure. And number 4 is using JAX to do MCMC. So I think it was on Tuesday or yesterday, I forgot. I sent you guys the link as how to download the JAX file. So please do that if you have your laptop. If today we get to that far, I can help out to see if you you have to install that package. Sorry, I should say you should have to install the software first, and then from R we can use this run JAX function. So that was what was the issue, I think, was before the break that I first introduced JAX, and then we all couldn't do it, and then I forgot about it. So now is the time to do that. And this going to be a small exercise later on, and then in the end, going to be a recap. So definitely not today covering all of this, but hopefully at least the first 3 we can. All right, so I'm not a big fan of Korean drama, so I don't know too much about it, but if you do, you might tell us more. So K-drama is very popular, not only in Asia, but in other parts of the world, including the US and Europe, I think. And they call it Hallyu, I guess. And it's literally just means Korean wave, okay? And in the US, you can use Hulu, Drama Fever, and Netflix, some of them. You can do online streaming of dramas. And the drama is being rated in Korea, so it's ratings, right? Like the higher rating means like better, I guess, preferred by the audience overall. So in Korea, sounds like there are 3 different main producers / companies, and each drama is made by one of those 3, and then they are broadcasted during one of the 4 different times of the week. Okay, so we're going to see the data a little bit more in detail, and then the particular ratings the particular student in the class collected is from the AGB Nielsen Media Research Group, and they collected, she collected the national AGB TV rating. So I think there are a bunch of different types of ratings, but she focused on the national one. Okay, so what we saw, what we will see is a ratings of 11 different K-dramas, which were broadcasted between 2014 and 2016. All right, so I said earlier that there are 3 different companies. So the whole data set actually has, I think, like I said, 11 different, 101 different dramas and 3 different producers companies. So as you can imagine, if we're going to do analysis for all of the dramas, like from different producer companies, we can build up an even more complicated hierarchical model. But to start simple, we're going to focus on one particular company producer. Is the KBS, it's Korea Broadcasting System. So if we zoom in to this particular data set, there are only 33 dramas, okay? And I'm listing, I think, the first 9 here, just so you know how the data looks like. And I think it's listed alphabetically according to the drama title. Okay? So you can see the name. Some of them are interesting, I guess. I know one of those. The middle one, Descendants of the Sun, was so popular back then, so I watched a few. So, oh yeah.
Do you know what the criteria for rating is?
I don't know. Yeah,
Okay.
I don't know. Yeah, but good question. So one thing I can. So I mean, FYI, I probably would just share the poster that student made anyway, because it can be a good instruction as how you can make your poster. And probably in her poster, she talked about how the ratings are. I don't know the detail. Yeah.
Okay.
And yeah, sorry.
That's okay.
But I think the higher the rating, the better. That I think I'm sure. But anyway, so yeah, so there are 33 dramas in total. And earlier I said there are 4 different schedules that a drama is being broadcasted. So I think I coded by 1, 2, 3, 4 here. So the schedule, if it's 1, it's Mondays and Tuesdays. 2 is Wednesday and Thursdays. 3 is Fridays, and 4 is Saturdays and Sundays. And so that's what you see in the second column of the schedule that's being broadcasted. Okay. Third column is the ratings themselves. I think the range is from 0 to 1. Okay. And the date, I think it's the date of the first day of it being broadcasted. So that's, again, it was between 2014 and 2016. Okay. All right, so this is how the data is structured. And I uploaded the data set to Moodle. So it is the data set contains the whole 101 dramas in the data set. But in the script that I provided, I did a subset and then only looking at the KBS dramas. Okay? But then the schedule is being coded in the way that is shown here in the data set. It's a categorical variable. All right, so the first thing, I mean, if you want to do some kind of analysis about ratings, in particular, it's a continuous variable. So the first thing that we can do, if you want, is just looking at the ratings by different schedules. And so that's what I did here. The code is on the left, and yeah, so the first one is reading the whole data set. The third line is trying to just to subset to get the KBS drama. And then the ggplot is used to plotting different, ratings of a different schedule. So if you look at the rating on the right, what stands out, I mean, from the graph to you? I mean, it's color-coded and, yeah, color-coded, trying to use the density. I mean, it's smoothing a lot because we don't actually have a lot of observations. Yeah, it's doing a strong smoothing here, but you can see roughly how the density looks like. And the rating on the x-axis, I mean, again, even, yeah, I don't know exactly, but I think for this data set, it goes from 0 to 0.3, so that's the range that I put down. So anything stands up. I mean, this is part of Explorer data analysis. Usually we do this in order to shed some light on what kind of model that you want to do. So for this data right now, what stands out and what implication that you have, or this gives to you about the modeling approach that you might want to take. Yeah, Tyler?
Well, in terms of the data, it looked like on the first 9 that we looked at, no one aired on time 3 on Fridays. And also, if you look at the ratings on the density plot, Friday ratings are very bad.
So that's 3, right?
Right.
Okay, so that's the big one on the left.
Right.
Okay.
It also could be because it's just one day.
Yeah, good point. So yeah, so if you actually are playing with the data now, you will see how many observations there are. If I remember correctly, I have it on the slide later. I think there are only 3 dramas being shown on Friday for this KBS subset. So again, you are right. It's pretty coarse, and then I think it's only 3. So you see, I mean, it's probably not surprising that you see those 2 bumps here. It's a very small subset here. Okay, but overall, you do see that schedule 3, which is on Fridays, seems to give, I mean, who knows, maybe it's because of Friday, maybe who knows what it is, but it's lower than most of the other ones, right? I mean, the other three. Anything else? What about the spread? I mean, again, you will see that we're trying to use a normal model. We're going to look at normal models, I should say. And then for normal, we care about the mean and the standard deviation, right? So I think we all now have the idea of sharing across groups, in this case, across schedules. So I think it's probably interesting now, just by looking at the density plot, how if you were to share, say, mu and sigma, which one do you want to share, or which one you don't want, or whatever that your idea would be. Sharing meaning that they come from the same distribution, which is the prior that we're trying to do, right? So schedule-wise, the mean, I think, might look different, right? Variance, I would say, as well. But looks like between 1 and 2, I mean, the means and variance are not that far apart, right? Whereas number 4, much flatter, and I would say wider, but probably wider just because it's okay. And then, of course, 3 is very concentrated, but we know that it's a small sample size, so we have to take into account that as well. Yeah, so that's the thing. So you see that the total number of observations here is only 33, and then once you look into different schedules, it's going to be even smaller in each case. So this will be typically difficult task to do if you're trying to do it from a frequentist point of view, just because the sample size is going to be too small. But in Bayesian, we are able to actually still do the modeling like that we used to do. It's just like the sample size is small, you wouldn't, I mean, it's probably going to be a little contribution from the data, which means like the prior might dominate. So that's another thing we need to keep in mind. But I do want to like show you early on that sample size is small. Sometimes you only get one sample observation in a particular schedule or a particular group. And then that, in fact, I think is not doable in a frequentist setting. Whereas here, soon you will see that we can still put a normal density for that particular schedule. In this case, for example, schedule number 3, and still put a density, we just observe 3 observations. But it still makes sense. You can still do that with a small sample size. All right, so keep this in mind. And yeah, this is the table that I produced, just trying to look at it a little bit more in detail. I mean, you should look at this together with the plot that I showed you earlier. So here you see the minimum, the mean, and the max of the ratings for each schedule, and also the standard deviation. Okay? Standard deviation, I put it here. Also just to say, I mean, from the plot we see it, but also like numerically, you can start to look at whether sharing the standard deviation makes sense or not. Okay. And of course, the sample size. Yeah, so for number 3, I mean, schedule 3, it's only 3 observations. And there are 2 more in the other ones. And we can see that, I think, earlier from the plot as well. Okay. All right. So with this in mind, I think, at least tentatively, I think it makes sense to develop a schedule. I mean, there are schedule-specific normal models, and then there are 4 schedules. So in the end, we can start thinking about 4 different models. And so now you start to see that we don't label data by like yi anymore, because back then you have IID observations, and there's no group or like schedule specific information. However, now, because we know those observations are grouped in a particular way, so we can start label data using 2 subscripts. Here I'm using yij, and I think I'm using j to indicate the schedule. So j goes from 1 to 4, and then I is the label for the index of the observation in the particular schedule. So just start to think about the dimension of the data, because as soon as we go to next how to do the modeling, you will start trying to write the data model and then the prior, et cetera, et cetera. So it's important to keep in mind. And we do have 4 different schedulers in this case. All right, so the second part here is now we know observations are in groups, and we see some similarity, we see some differences across the different groups in terms of the observations. So let's just discuss quickly of what we know so far. Like say a couple of different approaches to modeling, and I want you to think about the pros and cons of each, and then hopefully we can arrive at the hierarchical model in the end. Yeah. So here the data we have is naturally like grouped in groups, but there are many other cases that observations arise in groups. For example, students' test scores from multiple schools, and then ratings of movies of different genres. Also, like here, ratings of dramas of different schedules. And I think when Josh was presenting his research, then I think it was, I mean, there are multiple grouping happening, right? One is about the cognition, known words, novel words, and scrambled words, right? So those are the different conditions that they're trying to do experiment about. And yeah, and another type of grouping is about the different letters, right? It's N, I, W, right? So then there are certain things. I mean, you can think about N, I, W, 3 as separate, but I guess you can also think about N as the unpredictable letter, right? And then I and W supposed to be the predictable letters, just because of the setup. Okay? So again, you can see that data can arise in groups, and then sometimes the groups are gonna have like some crossing. For example, here, we're only looking at the KBS data set, which is 33 observations from that particular producer. But I told you earlier that there are 3 different producers, right? So if you look at the whole data together, which you're welcome to do, the data set is available on Moodle, you can also start to see, I think, the grouping happening at different angles. One group is what we are having here is the schedule, right? You have observations going to different schedules, right? And another type is, I think, observations coming from different companies, right? So the whole model later, if you ever want to do it, well, feel free to do it, is you can start to think about, I mean, you can put a lot of different ways to think about the hierarchical, and then the sharing can happen maybe across schedule, maybe across different companies. Yeah. So those will be a good thing, I think, to keep in mind. But of course, I think doing a small exploratory data analysis at the beginning is always helpful. So you can like plot the data in different ways, and then that can give you some idea of how you want to model your data. Okay. So so now from now on, we're going to do Yij here, and J is the group index, and I is the observation index within the group. So I use Nj for the number of observations in the Jth group. Okay. So the sum of the Nj is going to be N, which is 33. Okay. And then J goes from 1 to 4. All right. All right, so I've been saying that we can use a normal model, and the reason is the outcome is supposed to be a continuous variable, so we can start thinking about the normal. So I posted 2 approaches here for you to think about. One is I'm just going to do 4 different models all separately. Okay? If I do that, my model can be written in equation 2. So it's Yij, Iid, right? Following a normal distribution with a schedule-specific mean mu j and a schedule-specific standard deviation sigma j. Okay. So those are all separate. And the other one is, okay, I don't know, we can just put everything together, and then the Yij will be Iid from the same normal distribution with mu and sigma. So for approach 1, we're treating 4 models separately. So we just have 4 different models going on, and we do the regular thing that we used to do, right? And then for approach 2, even though right now we're labeling as Yij, but just because of the way equation 3 is set up, you don't even need to worry about J or I. I mean, it's just one index because we're treating everything as Iid. Okay? So I want you to, just talk to your neighbors a little bit, just think about, we already know something, about hierarchical modeling, so you probably have some ideas of maybe you don't want to do approach 1, or maybe you don't want to do approach 2, or maybe one of those two or both of them still have some merit. So I want you to just have a quick discussion, and then we can look at the pros and cons together as a class. Okay, anything? Pros and cons of each? You can comment both at the same time, or just one by one. Yeah, question.
So there's like I think there are 2 ways of assessing this. There's like a data-driven way where you like actually look at your exploratory plots, and if you see like they mostly align, then you can be pretty sure that all of them can like share parameter values. And I think the second thing is your actual outside knowledge of the phenomenon you're studying. If you expect like systematic differences between like let's say certain kinds of like days or like schedule times, then you'd want to use different parameters to model.
Yeah, so I like the way that you said it, like data-driven way. So that is related to the exploratory data analysis that we did, not only the plot but also the table. And then of course, outside knowledge. We've been talking about using outside knowledge or prior knowledge into the prior, right? But sometimes those can actually go into the data model as well. So it really depends on how you think about it. So good. So if I go with approach 1. What kind of advantages do you think there is? And what about disadvantages if I do that? Just, without thinking about the data, just think about the model itself, the assumptions that we're making. And same goes for approach 2.
For 1, we could probably look at each day separately or like grouping. And so then you're like accounting for like differences that might occur as a result of that. Then the drawback is, like you said, like we only had 3 samples for Friday. So it might not be the best way to go about it because we don't have like a big enough data set to work with.
Yeah, good point. So I think, so indeed, I think schedule 3, there's only 3 observations. And earlier I was saying that you can still do it in the Bayesian framework, but as you can imagine, even though you can do it, the variability will be large just because you have a really small sample size. So then if like either from the data-driven idea or just like outside information idea that Christian mentioned, if you think, say, the means probably are coming from the same distribution, if you think so, then you can actually, what we usually like to call as borrow information across different schedules, so you can make like better inference for each of the schedule themselves. And then it actually, I think particularly for those observations, for those schedules with very small number of observations, then that can be a good contribution. Okay, sounds good. What about approach 2? Approach 2 is just you put everything together. You think everything follows the same distribution, right? So this is, ultimately, if you do like, how can I put it? Like, it's not hierarchical, but then this is the most pooling information that you can do, right? Sometimes you might went too far. I don't know. We don't know for sure. But then for this case, this will be the ultimate level of pulling information together. And then this totally ignores the subtle differences across the different schedules. So you can see, I would say, pros and cons. So I listed a few, but I think similar what we just discussed overall. And approach 1, again, I think groups with small sample size might suffer the most. And in this case, we don't have super small. We have like as small as 3, but sometimes if you only have 1 observation, then it will be very hard for those schedules. Right? And then of course, approach 1 also means that there is no connection between groups. Each like not like how to say, or a drama, like a rating of a drama for one particular schedule has nothing to do with a drama from a different schedule. Okay. And then, approach 2 is saying that they come from the same distribution, which is fine. But then let's see if we can find somewhere in between that we don't totally assume that they're all the same as approach 2, and we don't totally assume that they're all separate as approach 1, and somewhere in between is what we have learned roughly a little bit already. It's called hierarchical modeling. So we know the general idea that we're trying to share information, okay? And by assuming the same prior distribution for a certain selection of the variables, certain selection of the parameters. So what we're going to do now is go into the detail to see it. I mean, even though we know that we can put the same prior distribution for a same or a particular set of parameters, we still need to be super clear about the assumption that we're making. Okay, so when you're saying that they follow, so for example, if all of the mu j's, if you think they come from the same prior distribution, you're just going to write, say, like mu j, and if we're going to do a conjugate prior, you might be guessing we're just going to put a normal for it, right? Like what we've been doing so far, because that's the mean parameter in the normal model. And then if you assume all of the mu j's coming from the same distribution, it's not saying that they're exactly the same, right? It's just saying that they come from the same distribution with the same mean and the same standard deviation. And then, of course, how can we choose that same mean and the same standard deviation in that? Because there are certain meanings. I mean, in the normal models, it's, I think, intuitive, because we know that the mean is the mean, the standard deviation is the variability. So you can actually control how much, like how strongly, say, for example, you think they're coming from the same distribution, and how variable they can be across the different means. Okay, so let's get there, and I think I will start with